So we're going to start off here with number 3. It says the polynomial listed right there gives the number of cans used in a display shaped like a square pyramid having a square base formed by C cans per side. Find the number of cans in the display if the square base has 7 cans per side. So what's going on here is someone has been nice enough to us to develop a formula. We didn't have to develop the formula. There's no geometry that we need to do here. We simply need to take their formula and use it. So it says that polynomial right there will give the volume, or give the number of cans in the display based on a square pyramid shape. And then it wants to know how many cans are there in this if we want to have a 7 cans per side square base. So the base is going to be 7 cans by 7 cans. We want to know how many cans we need. Let's think about why you would want to know this. Think this through. Like if you, like somebody at the, I mean, have you ever seen like at King Soopers, the displays they make with the cans, especially around football season? They make like football stadiums.
I think they did it with like boxes this year.
Yeah.
Boxes of soda.
So you could do boxes, you could do cans, you could do whatever you want, right? Chip displays, displays of salsa. It might be handy to know how many cans to bring out of the stock room to make this thing with, right? So this could be a potential help as far as, you know, minimizing the time spent on this display. So we know the formula. We know that we want to have 7 cans on that the side of the base. What do you think we do here? What do you think? Yeah, go ahead, Christiana.
Plug in 7.
Yeah.
For C.
Yeah, plug a 7 in for C. I'm going to suggest here that maybe we use the calculator to help us out. But it should look something like this. 1/3 parentheses 7 to the third plus 1/2 parentheses 7 to the 2 plus 1/6 of 7. So grab your calculators and let's figure out what that is. Avery, question.
I'm going to buy you plug in 7 for each C. Because, like, aren't the levels, like, different?
They are. But what that polynomial, we're told, and we didn't see the proof of this, we're told that polynomial gives the number of cans used in a whole display based on having a square pyramid shape. So someone has gone to the trouble, and we could develop this, I suppose, if we wanted to, if using the volume formula for a pyramid, a square pyramid specifically. We can investigate that if you want, for sure. But we just have to trust that that's true at this point. That the number of cans in the whole display is given by that polynomial. If you want to go to the geometry, we certainly can. Are you sure?
Yeah.
Okay. Yeah. Anyways. Okay, so you're using your calculators. Did you come up with an answer?
I'm close to it.
1/3 times 7 cubed plus 1/2 times 7 squared plus 1/6 of 7.
140.
140.
Okay.
You guys agree with that?
Yeah.
140. So, again, the usefulness of this is, you know, you're the manager of the store, you want this display, use this formula, you say, all right, employee, please go get 140 cans from the stock room. Let's try to build this thing. That's what you do. Okay, any questions there? Just an evaluation of a polynomial idea? Yeah, go ahead.
Just evaluate this. The picture doesn't have 7 cans. It actually has 10 cans per side.
Well, see here. I see a 4 by 4 base, don't you?
Yeah.
So when it says per side, it's talking about only the base. And maybe this is kind of what Avery was talking about. So this is not the complete display, right?
Yeah.
We'd have to broaden out that base quite a bit for it to match what we did.
That is not 140 cans.
No, it is not. I would agree with you there. Okay, yeah, Hunter, go ahead.
So can't we just add up the C's and the 1/3, like make it all the same denominator?
Well, we could consider that, but I don't think we can because these are all unlike terms because the variables have different exponents. The variables are 3, 2, 1.
If they were all C?
If they were all like C to the firsts, then yes. Or if they were all C squareds or something like that, then you certainly could.
Okay.
Good question. Anybody else with a question? Yeah, Amelia, go ahead.
Could you make it 1/7 cubed? Could you do that? Like,
1.
7 over 1? Not 1/7, sorry.
7 over 1? Yeah.
And do that? Okay.
Why would you want to do that?
I don't know, it just seemed like easier.
You don't have your calculator.
Now I'm a little bit lost. How would that make it easier?
I don't know, I just thought of it, so.
Yeah, so let me make sure I understand what you're saying. You're just saying, let's just go 7 over 1.
Yeah.
To match the other fraction. You know what? If that visually helps you, then I got no issue at all. I don't think it's necessary at all, but if that helps, do it. Yeah, definitely. No question. That if that helps you, do it. Okay, anyone else? Fantastic. Okay, good job. Let's move on to our next one. So, as always, I think your best bet is to replace all of your C's and D's with empty parentheses and then plug from there. So I'm going to evaluate by doing that. 2 parentheses squared, parentheses minus 5 parentheses, parentheses squared. You're going to be very careful that you're plugging things in where they're supposed to go. So C is -3, so I'm going to plug the -3 in here and here. D is -5, so that's going here and here. Question? Oh, yes, yeah, go ahead. All right, order of operations. Let's do the exponents first. It's going to be 2 times 9 times -5 minus 5 times -3 times 25. And then we do the multiplication. So 2 times 9 is 18, and 18 times -5 is -90. Minus, you could do this in a number of ways, I suppose. But 5 times -3, actually, I'm going to go -3 times 25 is -75. -75 times 5, 3, hold on, -75 times 5, 35, -375, right? So minus -375, so that's really plus. And so those of you that were shouting out 285, I think we all agree. Okay. So you doing okay with those, right? You're squaring the negatives okay, keeping the order of operations straight. Good? Well, let's see how good you really are. Let's go to the board.
Oh, yeah. Hakuna Matata.
We will definitely revisit this later on in the year, but for now we're just going to we're going to create a table to create a graph. Okay, and so the first one I want to graph here is y equals x squared. Might be something you're familiar with. Does anybody recognize that by any chance? You've maybe seen it before. What do you see, Hunter?
I've seen it before.
You
I've
have-
seen these before. You like have to put in different numbers for X. And then
Yeah, definitely. We're going to put in different numbers for x, but I'm wondering if you recognize y equals x squared specifically.
I
It's okay if you don't.
think so, but
It's not any requirement. I'm just kind of curious. Okay, so let's plug some numbers in for x. I'm going to suggest these numbers here. This will give us a good picture of this graph. Let's go x equals -2, -1, 0, 1, and 2. So let's be working on completing that table with the outputs, right? So you're going to be plugging the -2 in for x, squaring it, getting an output. So any suggestions? What if what if we plug in the -2? What do you think the output is? Go ahead. 4, yeah, specifically positive 4. What if you plug in a -1? No. -1 squared, it'd be -1 times -1. It'd be 1. What if you plug in a 0? 0 squared is 0. And how about the last two? The 1 and the 2 become a 1 and a 4. So the outputs are 1 and 4. So if you remember from before, that each one of these data points in the table represents an xy coordinate. So the first xy coordinate is -2, 4. So we can graph this by plotting that point. So let's see here, -2, 4, I have right there. And then -1, 1 is right here. So far, it just looks like a regular old line, right? But then 0, 0. That's right here. What do you see taking shape at this point? It's starting to bend a little bit, right? And then when you graph the last 2 points, you can see that it was a significant bend, right? 1, 1 is right here. And 2, 4 is up here. There's a couple things to notice. Do you notice the symmetry? There's nice symmetry about the y-axis, and it does curve. So if we were going to try to graph this actual shape here, we would try to connect the dots here, but connect them with as smooth as we can, curve. So that could look something like this. Let's start over. How about this?
then actually it goes up to the 3x is 9.
Yeah, the plus minus 3 gives you 9s. Yeah, that's right. Does anybody know what to call this shape? Parabola. Good. Yeah, this is the name of this shape of graph. It's called a parabola. And like I said, we'll do a lot more with stuff like that in the future. But for now, just a little bit of table input output with the evaluation will give us a good look at what the graph would look like. Yeah.
I think there's something wrong with my calculator.
What?
I put in -2 squared.
Yeah. So you made the same mistake that she was talking about.
Oh,
That's not squaring the -2. That's squaring the 2. Yes, sir.
We did this project in 8th grade where we did like an everyday thing.
Ah.
Make parabolas to like make them like the.
Well, they do. The Angry Birds do follow a parabolic
Sorry.
pattern of motion. Yes, they do. Yes, they do. That's a fun game. I like that. Very cool. Okay, so now let's move on to our next graph, because not all polynomials look like this. They're not all parabolas. Evan, would you mind sharing the outputs for your table?
I got -2, 0, -1, 3, 0. I got 4.
Oh, sorry. Are you telling me the inputs and the outputs?
Yeah.
Just go left to right on the Y's.
0, 3, 4, 3, 0.
Okay. You guys agree with Evan's table? Sir, I'm really asking you the question. Do you agree?
Yes.
You got the Rocky agrees, Amelia agrees, Christiana, you agree too? Everybody agrees?
Yeah.
Okay. Looks pretty good. Okay, so then did you guys take it to the graph? If you didn't, you can do that now, but let's see what this looks like. So let's see here. -2, 0 is going to be right about here. And then we have -1, 3 is right about here. 0, 4 is here. We got 1, 3 and 2, 0 are here and here. So do you see a familiar shape showing up?
Yeah,
Does that look like a parabola again?
it does.
I think so. The parabola has definitely changed. How is this parabola different from the one we just did a few minutes ago? What is it, Amelia?
It's facing down, so opening up towards the bottom of the graph.
Yeah, opening towards the bottom instead of opening towards the top. It's been moved up a little bit too, right? So guys, I want to give you a general conclusion here. This is really important. What is the degree of this polynomial?
2.
The degree is 2, right? Because x squared, -x squared. What was the degree of the previous polynomial? Because it was x squared again. So here's the general rule. If the degree of a polynomial is 2, its graph will always be a parabola. Every single time. If the degree is something different, it won't be a parabola. But if it's degree 2 polynomial, the graph will be a parabola. Let's do our final one here, and then we'll be done. It's the last one on your notes. Of course, you can see from the polynomial, this is not degree 3. Or not degree 2, it's degree 3. It's a little bit different. So I think the same inputs are going to be okay here. -2, -1, and 0. And then 1 and 2 to finish that out. So take a minute, see if you can fill out your table with those outputs, and then we'll check it and try to get it on the graph.
I have a quick question.
Does anybody have the output for -2? -10 is right. Nice job. Any questions on that one? I can show you the steps there. All right. Does anybody have the output for -1? Amelia? -3 is good, yeah. Nicely done. And then how about the output for 0? -2. And let's try to finish this out. Anybody have the output for 1? -1. And then the output for 2 is? Should be 6. 8 minus 2. All right. So now we go to the graph, and I imagine you've already seen this looks a little different than those parabolas we did a few minutes ago. So my first point is -2, -10. That is way down there at the bottom of the graph. And then -1, -3 is here. Oops. Right there. 0, -2 is here. You can see a bend. Do you see how it looks like it wants to be a parabola? How it wants to like start bending and then drop back down. but of course it doesn't do that. 1, -1 is here, and then 2, 6 is way up here. Okay, so you can see there's a significant bend to this. What this graph looks like, we connect it with a smooth curve, something like this. Kind of missed that one. Let me try again. There we go. Put arrows on the end of it, and there's your graph. So when it's degree 2, the graph is called a parabola. When it's degree 3, like this one,
Triabola.
that's a cool name. It's not it, unfortunately. Palabri. It's actually called a cubic.
Oh.
That's a cubic graph. That's what you would call that. Hey, let me ask you one question, and then I want to show you a shortcut in the last couple minutes here. What if you have a polynomial of degree 1? What do we call that? A line.
Line.
Y equals 2x plus 4. That's a polynomial of degree 1. That's just a line. Okay, so if you don't mind, I want to show you guys something. You know, I'll tell you what. Why don't I show everybody this thing? Let me just use the old calculator here. Yes, here's what I want to do. I want to show you how you can work with a table and make it easy to work with the table. So this kind of goes to a question that Jake asked. Maybe you've seen this, maybe you haven't. If you need to create a table, you can actually use your calculator to help you significantly with the details. Are you guys all watching?
Yeah.
Check this out.
How'd you get there?
Y equals. So yeah, let me start over here. So you turn your calculator on, you're just on a blank screen or whatever, just push Y equals. What I'm going to do is I'm going to do that x cubed minus 2 that we did there. This is a huge time saver for you potentially. I'm going to go ahead and input that in for my Y equals. So it's going to be Y equals x cubed minus 2. And then if you look carefully on your calculator, right above the window button it says TBL set. That stands for table setup. So I'm going to go ahead and click on that and see what my table setup looks like. So my table, look at this, actually I did not plan this, but this is working out beautifully. It says table start -2. Isn't that when we started off with our inputs? -2. And then delta table means change in table is 1. That means it'll go up by 1 for each little spot in the table. And so my table setup is somehow already exactly what I want. You might have to change that at times, but this is what I want. And then to see the table above graph, you see it just says table. So check this out. Second table, -2 has an output of -10, -1 to -3, 0 to negative. You see your table right there, don't you? It's right over here. You see it in larger format right there. So if you can remember to use how to use that table setup and table tool on your calculator, it could take a lot of those calculations and make them very, very easy for you as long as you know how to push those buttons. So encourage you to do that. If you want, you can do it the old-fashioned way too. One thing I will not do, you're taking your quiz, on February 6th, you're taking your quiz. If you come up to me and say, in the middle of the quiz, you say, how do you do that table thing again? I'm going to say, yeah, should have figured that out before you showed up for the quiz. So please have, if you want to use that, please have that figured out ahead of time. We'll maybe practice that a little bit. So, all right, I hope that you have a wonderful day and weekend. See you on Monday.